Section 2.2. These notes are titled Power Functions and Modeling. Modeling, of course, means word problems. And the word problem, we're going to go ahead and get out of the way right there at the bottom of the notes. That is the one skill in this entire note set that you need for the Chapter 2 test. It doesn't mean the rest of it's not worth knowing. Again, all knowledge is worth having, but the modeling, so to speak, is going to be the only thing that I'm going to test you on. And it's really not going to be hard. So what exactly is a power function? Any function that can be written in this form, notice that there is no pluses or minuses anywhere, k times x to the a, where k and a are non-zero constants, so neither k nor a is allowed to be zero. This is a power function. A is the power, the exponent, and k we call the constant of variation or constant of proportion. Now these are terms that you are supposed to have learned a long time ago, I think in 7th grade math, where you say inverse and direct variation. This is a term that was supposed to have been covered in 7th grade math. Don't worry, it's not hard. What we say is that f of x varies as the 8th power of x, like the 3rd power of x, the square root of x, something like that. Or we could say that f of x is proportional to the 8th power of x. Letter A, not the number 8th. That's a weird thing to say. But anyway, I could say that we could say that f of x varies inversely as the 3rd power of x, or varies directly as the 3rd root of x, things like that. Okay? Or I could say varies directly, or I could say varies inversely. Now there are 4 possible shapes for these things, for the general power function, but this is specifically for x being greater than or equal to 0. So we are avoiding any possibility of x being a negative number. Why, Mr. M? Well, because if x, which is the base, were a negative number, let's think about that for a second. A negative number raised to an even power is positive. A negative number raised to an odd power is negative, which means we would have a graph that is discontinuous freaking everywhere. I mean, think about it. What's a negative number raised to an even root? Undefined. A negative number raised to an odd root? Negative. I mean, so you would just have something that's undefined everywhere. I mean, there's so many places where it's undefined. So we're going to specifically talk about our base being positive or 0 only. In every single case, regardless of what x equals, as long as it's greater than or equal to 0, the graph will go through the point 1, k. And that should make sense why that's possible. If your base is 1, if x equals 1, it doesn't matter what power you raise it to, correct? You're always going to get back the number 1. So then you're going to get 1 times whatever k value is sitting in front of it. So 1, k exists on all of the shapes. Those with positive powers will also go through 0, 0. But why not negative powers? Well, if you remember back to Algebra 1, Algebra 2, your exponent rules, negative exponents, like say x to the negative 1, that's actually equal to 1 over x, correct? You cannot divide by 0. Therefore, x equals 0 does not exist whenever you have a negative exponent. So as long as the power is positive, you will go through 0, 0. If the power is negative, then you're going to have something that is asymptotic to both the x and the y-axis. So this image on the left, I've given you, and it's in color. Hopefully it's nicer to see it in color than it is when it's printed. But this is what you get every time the constant of variation, the k, is positive. And then you get the one on the right side anytime the constant of variation is negative. And that should make sense why that's the case, because it's just a reflection over the x-axis. So it's the exact same image, just flipped upside down. Cool beans? Cool beans. Great. I've shown you the possible shapes. So the green one is what you're going to get when your power is negative, like 1 over x. You get something that is asymptotic to both the x and the y-axis. The red one is what you get if a is a positive number. X to the 2nd, 3rd, 4th, 3.5, things like that. Any exponent that's a positive number. Yes?
Is it the same graph for like 2 and 3 or something like that?
for x equals 2 and x equals 3, or I mean a equals 2 and a equals 3?
Yeah.
It's the same general shape. It'll have different y values, obviously, but it's the same shape. So you get this red shape, which looks like a piece of a parabola or a piece of a cubic or anything like that. You actually get this kind of shape for any positive power bigger than 1. Cool? Okay. Now the black one is just the identity function. That's what happens if the power is 1. That's because you have f of x equals kx. It's just linear. And then the blue one is what you get for any positive power that's between 0 and 1. Like a third power, a 1/3 power, a 1/4 power, a 1/2 power. Basically what I'm talking about are roots. Cool? A hand went up in the back, but then it went down.
You said 3/4 when you had the one that was a is greater than 1.
Of course I did. See, like I said, I make a lot of mistakes. Sorry, yeah, 3/4 is going to fit here, obviously. Sorry about that. Yeah, and then the one on the right side is just a reflection of the x-axis, everything that's on the left side. So rather than just show you this image, I figured it'd be kind of powerful and good notes for you to see it changing. So I got Dr. Desmos fired up for us. And I have x to the a. Notice I don't have a constant of variation. Right now my constant of variation, k, is 1. I mean, I could type a 1 here if I wanted to, but it's not going to change anything, right? So right now the constant of variation is 1. The only thing that constant of variation is going to change is whether or not I vertically stretch or shrink this image. Because remember, multiplying by a number on the front is just a vertical stretch or shrink. Vertical stretch would be any number that's bigger than 1 for the constant of variation on the front. And a vertical shrink would be any number between 0 and 1 for my constant of variation. Cool with that idea? Transformations type stuff? Awesome. Here I have a slider. And what I've done is I've set it to begin with a equals 1. That means I'm just graphing y equals x. That's what you're looking at. Now as x goes any number bigger than 1, I get curvy. Pretty neat, huh? And of course, the larger the exponent gets, the steeper the graph gets. And that should make sense. That's because, well, numbers get big really, really fast with bigger exponents, right? But what about numbers between 0 and 1? Let's see. Creep it back down to 1. Now numbers between 0 and 1. Boink. Now they start to look like third roots, fifth roots, 3/4 powers, things like that. Any number between 0 and 1. And of course, sometimes these would be double-sided graphs, but we're specifically talking about bases, x values, that are positive or 0. Now let's creep it down to 0, which should make perfect sense. X to the 0 is just 1. Now let's check out negative exponents. See, asymptotic to both axes. And once again, the more negative this thing gets, the steeper it becomes. Where's negative 1? There's your classic 1 over x. But we're only looking at the positive side of it. Now what I have down here is just the reflections over the x-axis. Boink, there you go. So it's the exact same image, just reflected over the x-axis. Again, asymptotic to both axes as our exponent is negative. And when your exponent is between 0 and 1, you have something that looks like a piece of a root graph. And anytime your a value exponent is bigger than 1, you have something that looks like it could be a piece of a quadratic, a cubic, a fifth power, things like that. Neat? All right, back to the notes. Power function formulas with positive powers are statements of direct variation. Really important concept right there. If the exponent is positive, this is a statement of direct variation. And things with negative powers are inverse variation. That's really important that you know that. That's the one skill that you're going to need for the Chapter 2 test. Direct variation, positive exponent. Inverse variation, negative exponent. Got it? Yes? 0 exponent is, x to the 0 is just 1. So you would just have remember when on Desmos when I had that straight line at y equals 1? That's it's no variation at all because it's constant. So positive exponent, direct variation, negative exponent, inverse variation. Yes, ma'am?
So like on the test, would we have like an example of like a graph and we'd have to say if it's negative or
No, you're working way too hard. It would be a word problem like this. I will not have you graph power functions at all on the Chapter 2 test. Because guess how you graph power functions? with a calculator. You don't try to do them by hand. It's not worth your time. Now, we will in the notes today because all knowledge is worth having, but in reality, nobody does it by hand. From empirical evidence and the laws of physics, it has been found that the period of time, capital T, for the full swing of a pendulum varies as the square root of the pendulum's length L, provided that the swing is small relative to the length of the pendulum. It says, express this relationship as a power function. It didn't say the magic word, varies directly, but because it didn't say varies inversely, you automatically assume direct variation. If it does not say inverse variation, it's guaranteed to be direct variation. So when it says it varies as, let me grab my highlighter. When it says varies as right here, I go, oh yeah, it didn't say inversely, so that means directly, direct variation. It says express this as a power function, capital T, and we're talking about the pendulum's length. L is our variable. So the time that it takes with respect to the pendulum's length is. It says varies. So I told you varies directly. Well, we need a constant of variation. We don't know it, but we're just setting up the problem. Our constant of variation times x, and we know we have a positive exponent because it says, does not say inversely. It says varies as the, square root. The square root of x. I've been told to express this relationship as a power function. That means it needs to be kx to some exponent. So what would that exponent be? What is the square root as an exponent? It's 1/2. Yeah. And there you go. That question is solved. This is the only kind of question from this unit that is on chapter 2. But let me explain to you what that question would look like. I would have given you one of the coordinates. Let's just say I tell you, and the coordinate 1, 6 exists. What is y when x is 3? So what you would do is you would use the coordinate I give you, which is an x, y. You would plug it in to solve for k. Then once you know k, you plug in the other information I give you to solve for unknown information. And don't worry, that will come up on 2 different practice sheets before the chapter test. Okay? Yes?
Can you? So if there is like you give us line 6,
Mm-hmm.
and then you find that it's like
You find k.
you find k,
Yeah.
and it's like +2.
What?
It's like +2.
Okay, k is positive. All right. That. Yeah.
Then like how would you write that equation?
You would write 2x to the 1/2.
Okay.
You're overthinking this.
Okay.
Hey, if I will give you a coordinate, an x, y. You will plug in x, you will plug in y, you will solve for k. Once you know k, you just write the equation, but instead of writing k, you write whatever number you found it equals. Then you'll take the other information I gave you, say I give you another x and tell you to find a y, you plug that x in and you solve for y. It's really not hard. Like you said, it will be on 2 different practice tests before the chapter test. McKinley.
An example, please.
Sure. So let's say 4, I'm going to make my life easy, okay? I'm going to say that 4, 8 is on T of L. What is x when y equals, I don't even know. I'm just going to make something up and I hope it works, okay? 10. Just put me on the spot. So let's go ahead and use the knowledge we have to solve for this unknown k now. Well, I've just told you that the y value is 8. That's T of L is 8. So you go, great. 8 equals some unknown k times the square root of, well, x was 4.
Wait,
what's
how
this?
did you know what was the square root of?
Right there. Because it said square root right here.
So the equation would tell us what a would be, or have us figure it out.
I would have to tell you that they vary directly as this, the square of x or the cube of x or something like that, I have to tell you the power.
All right, I was wondering how we were going to figure out the power.
Yeah, basically you have to be told what the power is. So then for that one, okay, square root of 4 is just 2. So what you have here is that 8 equals 2k. So now you know that k equals 4. All right, well, if k equals 4, then you just plug that in as a number that you know. It's not an unknown anymore. So now you can say T of L equals 4 square root x. And then I go, yo, what is x when y is 10? So then you would plug 10 in and solve for x. And at this point, we just solve for x. So you divide both sides by 4. And that gives us, and you'd have 10 over 4, which reduces to 5 over 2. 5 over 2 equals the square root of x. And you cancel the square by squaring both sides. You cancel the square root by squaring both sides. No pluses or minuses required here. Remember, x must be a positive number in order for it to be a power function. And it wouldn't matter anyway because you only get square roots when you cancel a square. Excuse me, you only get pluses or minuses when you cancel a square with the square root, not the other way around. So this would tell us that x equals 25 over 4. There. That could be a test question, just like that. And like I said, it'll show up on 2 different practice sheets before the actual test. For these, we've been told to state the power and the constant of variation for the function. Graph it, analyze it. So we're going to sketch it, and when you are home tonight doing this work, you'll use either Desmos or a graphing calculator, and you'll just draw a quick sketch of what you had. What's more important here is the analysis. So I'm just going to give you the graph because I expect you to use graphing technology. You guys cool with that idea? I expect you to use graphing technology. Nobody really graphs power functions by hand. It's not really worth your effort. But analyzing it is important information. Well, this isn't written as a power function until it's kx to the a, right? So the number in front is just a 1. But our exponent, instead of saying third root, you could say is the 1/3 power. So the constant of variation is 1. And the power is 1/3. There you go. Now remember, we're only using when x is greater than or equal to 0. Well, that means the left side of the graph doesn't exist. Left side does not exist. This graph would sketch like this. Whee! And it would be defined at 0, 0. Because you can take the third root of 0. It looks something like that. And as far as the analysis is concerned, we would just say things like domain and range, you know, whether or not it's continuous, where it's increasing, things like that. Now, for some reason, the textbook did not say, oh, by the way, x has to be greater than or equal to 0, even though it's a power function. Because technically, the third root of x looks like this. This is the true third root of x, right? You can take the third root of positive and negative numbers. So I'm not gonna lie, I'm a little confused in this example by our authors. Because our authors give us the whole graph, but they defined power functions in the definition by saying that x must be greater than or equal to 0. So I'm not really sure what they were thinking, so I'm just going to ignore that stuff, because remember, for power functions, the base, x, must be greater than or equal to 0, or strictly greater than 0. Let's just say it like that. So what would I want to say? What is its domain? Well, its domain begins at 0 and heads to the right forever. Its range, y values, well, guess what? Begins at 0 and heads up forever. This is considered a continuous graph because because it doesn't have any discontinuities. It is continuous. We've restricted the domain, so we kind of got rid of discontinuities. It is an always increasing function, so it's increasing over its entire domain. However, remember you can never include endpoints in your increasing and decreasing, so it does have to have a parenthesis on it. So it increases forever, and since it has a bottom, it is bounded below. We could say it has a minimum, but that's kind of given by saying bounded below. Cool with that idea? All that makes sense? That's not bad, right? Especially since I'm not going to make you graph it yourself. Just remember that when you go to graph these, x must be greater than or equal to 0 by definition. 1 over x squared. Again, authors completely ignored their own definition of a power function. They gave you positive and negative x's in the graph. I'm not going to. I'm only going to be looking at the positive x's. But I want to write it as a power function. Well, you could bring that x squared up to the top and make the exponent negative. So again, your constant is 1, but this time your exponent, your power, is negative 2. And sticking to the positive side of the graph. I told you and I showed you with Desmos that when the exponent is negative, the graph is asymptotic to both the x and the y-axis. And since my constant of variation is positive, this graph basically looks like this. Asymptotic to x and y. That's good enough. That's enough knowledge for this stuff. So its domain is from 0 but not including 0 to infinity because it's asymptotic. And the range is identical because it's asymptotic. Yeah, it's continuous. Doesn't have any discontinuity, so you could say it's continuous. But if you were riding this thing like a roller coaster, your roller coaster would always be falling. This is an always decreasing function. It decreases over its entire domain. And because it has a horizontal asymptote, the y-axis, it is also bounded below. But this one does not have any maximums or minimums. Oops, I forgot the word bounded. Okay, we'll just do this because I don't feel like erasing. Bounded below. Ta-da! That's enough. Okay? So when you're analyzing your functions at home, if you're checking your answers in the back, if you don't say all the things they say, like you don't use limits and you don't talk about symmetry, don't worry about it, okay? It's not that big a deal. This is easy though, right? Just use a graphing calculator, give me a quick sketch, and then just say some things about it. Give me domain, range, say it's continuous, give me where it's increasing, decreasing. If it's bounded somewhere, let me know. Those kinds of things, okay? Shouldn't be that hard. Please don't break your brains. So monomial functions. Notice that both of these have an integer power. That is not always required, but these two have integer powers. It says, describe how to obtain the graph of the given function from the graph of its parent function. So this one's parent function would have been x to the third, and this one's parent function would have been x to the fourth. So we're just going to sketch the graph and then describe the transformation. So what is that 2? What kind of transformation is that? And on part B, what kind of transformations are the negative and 2/3 going to give us? That's all we're doing.
But Mr. McCutcheon,
Yeah.
wouldn't it not be like that? Because couldn't k equal 2 for A and k equal negative 2/3 for B?
Well, that's
That
what
way
they
you're
are.
transforming.
So in A, the way they're sitting, k is 2, but its parent function would be k equals 1. So we're just talking about what kind of transformation. So the parent function is basically always going to be k equals 1 for a monomial function like this. It's like, remember back to algebra 2 when I was like, okay, the parent quadratic is y equals x squared. You know what I mean? And then I could put a 2 on the front and you go, oh, that's a transformation. It's the same idea. Anytime you change the front number from a 1 to anything else, that is some kind of transformation in every single function. So again, the authors used both the positive and negative side of the graphs, and I am going to 100% disagree with them here. If we're calling f of x a power function, we have to restrict its domain to only the positive side, and here's what you would have gotten. I'm just, again, it's a quick sketch, okay? Here is g of x. If I call that the parent function, on your graphing technology, when you graphed this, you would have gotten something that looked like this. That's f of x. And now you would just use your knowledge of transformations to tell me, if you multiply by 2 on the front, what kind of transformation is that? Vertical stretch, and you would say factor 2. So, you know, they brought transformations into this. Now the second one, again, you're using graphing technology. You're just drawing a quick, dirty sketch. Again, the authors gave us both the left and the right side. I don't know why. They're violating their own rules. Here's what x to the 4th would have looked like. The parent function g of x would have looked like this. So 4th powers look like quadratics because technically anything with an even exponent is a quadratic. So what I should say is that 4th powers look like a parabola. The only difference is it has its bottom, so to speak, is flatter for longer. And the bigger the exponent gets, the flatter the bottom becomes. So what would the negative on the front do? It'd flip it over the x-axis. It's a reflection. And that 2/3 being a number between 0 and 1, what would it do? It would be a vertical shrink, which would give it the illusion of being more wide, wouldn't it? So we would actually end up with something like this. Again, you're going to use graphing technology. So we say the negative sign is a reflection over x-axis. And you guys have already told me, I forgot my x. Squeeze it in there. And you guys have already told me that 2/3 is a vertical shrink. A factor 2/3. So it gives us the opportunity to review some older material. We are not going to let this section be hard. Graphing is our friend. All you care about is the word problems for the most part.
Will we have a graphing?
No, you want to have a graph calculator on a test because I'm only going to ask you a word problem, like from the front page. Because in all actuality, you don't graph power functions by hand. Do you know how to graph a decimal exponent?
No.
Exactly. Who does? You know what I'm saying? So it's not worth our brain power right now at this level of mathematics to try to learn how to graph x to the 2.3. Why bother? Could we do it? Of course we can. We're smart. But why bother? Yes.
So how many questions?
From this section, 1.
No, I mean like.
On the whole test, I don't know. I haven't made it yet. Ms. Klein and I need to get together and edit last year's test. We'll probably shorten it a little bit, and then I have to change all the questions, so I don't actually know. Come on, panel, catch up with me. There we go. Oh my goodness, more graphing. Okay. State the values of the constants a and a, or k and a. Describe the portion of the curve that lies in quadrants 1 or 4. Why quadrants 1 and 4? Because that's where x is greater than or equal to 0. So finally, at least the authors removed their heads from their rectums for this one. Determine whether f is even, odd, or undefined as x is less than 0. Oh, so at this point, what they're trying to do is say, well, hey, if x was negative, would the function be even, odd, or undefined? Okay. So we're going to describe what it looks like in quadrants 1 or 4, and if it exists in quadrants 2 and 3, we will sketch it and describe its symmetry if it has any. Describe the rest of the curve if there is any. Graph the function to see whether it matches the description. Okay, let's be real
Did
here.
you say it couldn't be in quadrant 3 and 4?
It could if you don't restrict the domain. So what we're going to do for this one is we're going to cheat a little bit because this is what I would expect you to do at home. Graph it on a graphing calculator first, and then give me all that descriptive crap. No one's asking you to describe the graph before you graph it. That you don't need to, okay? So cheese it, go directly to the graph, and then we'll describe it. So this first one was f of x equals 2x to the negative 3. Well, they all go, you know what I should have done before I came all the way down here? What a long walk. Is this. We can say what k and a are right now. K is 2, a is negative 3. And why do I care? Because all power functions go through the point 1, comma, k. That's why I care. So we know that this goes through 1, comma 2. We know that. And let's see, I gotta leave myself some space. So scoot that over. There we go. Okay. We know it goes through 1, comma 2. But hey, look, that is a negative exponent. And if we can remember all the way to the front of the notes, we said anytime we have a negative exponent, we have a graph that is asymptotic to both axes. Like this. We know it goes through 1, comma 2. So it goes through 1, comma 2 and then is asymptotic to both axes. So it looks like this. And if you'd graphed it on your graphing calculator, you would have seen that it also went through negative 1, comma 2 and did this. So if we have not restricted our domain, that is the image we get. Everybody,
Negative 1, negative 2, negative 1, 2.
did I say negative 1, 2?
Yeah.
Sorry, negative 1, negative 2.
Are we supposed to graph in quadrant 3?
That's what I'm saying. If it exists, we're just going to go ahead and sketch the graph. And then we go back and we do what the question said. And the question first asks us, after identifying what K and A are, is to describe its, what does it say? Describe the portion of the curve that is in quadrants 1 or 4. So now we're only looking up at quadrant 1, and we're going to describe that portion of the curve. Well, we've already seen an image like that, and we've already said that it's asymptotic to both axes, so we're going to say asymptotic to both axes. And if you were riding the roller coaster in quadrant 1, you're always falling. So it's decreasing in quadrant 1. So we just say asymptotic to both axes and decreasing. I don't know how to spell axes. It looks like axes, but whatever. So asymptotic to both axes and decreasing. That's what it looks like. Pow. Don't overthink it, please. Oh, and then it wants you to do talk about if there's any symmetry. It says determine whether f is even, odd, or undefined. Well, just look at the shape. If you reflect this thing over the x-axis, then reflect it over the y-axis, it lands on itself, doesn't it? You see that? That means it's odd. If reflecting over the x is the same as reflecting over the y, it's an odd function. So if I flip this thing upside down, or if I flipped it left and right, I would have gotten the exact same image. It didn't matter which axis I reflected it over. Because reflecting over the x is the same as reflecting over the y, it is odd. I almost said the wrong word. So you can just look at it and see that it's odd. Odd symmetry. Symmetry of 1m? I'm not sure. I can't spell. Yeah, that's wrong. I think it has 2 m's. Does it have 2 m's? Okay. Man, whatever. English is hard. If you know how to spell it right, you spell it right. Okay. Same trick. K, constant variation on the front, negative 0.4. Power, A, 1.5. all power functions go through 1 comma k. I know that's not how you spell that, but running out of space. 1 comma negative 0.4. Okay, let's go see what's up. You grab handy dandy graphing calculator and you type in negative 0.4x raised to the 1.5, and what you get is this. A graph that does exist at 0, 0. And the reason why it exists at 0, 0, because our exponent is positive, and it goes through 1 comma negative 0.4, which is like here. So it does this, whee, something like that. That's the whole graph. It obviously has no symmetry. And if you were going to describe that, you would just say it's decreasing.
It's bounded above too.
I'm sorry?
It's bounded above.
Yeah, they didn't ask for that, but it's true. They just wanted to know the description of it, but yeah, it is bounded above. But we know it's decreasing. It also goes through 0, 0. So it goes through 1 comma negative 0.4, and it goes through 0, 0, and the reason why is because the exponent was positive. If the exponent was negative, that would not have been the case. And then the last one. There's no number on the front of x, but there is. What number's in front of x? Negative 1. So our constant of variation is negative 1 this time. And our power is 0.4. Oh, look at that. Well, all power functions go through 1 comma k. So 1 comma negative 1. Awesome. Let's grab our graphing calculator, and by our graphing calculator, I mean my notes that are in my hand. Well, the front number was negative. That means on the right side of the graph, it's going to be in quadrant 4. And it has to go through the point 1 comma negative 1. So it's going to look something like this. It doesn't have a choice. It has to hit 0, 0 because the exponent is positive. And it has to go through 1 comma k, which happens to be 1 comma negative 1. But if you were to graph that in a graphing calculator, what you would have gotten was this. Does it have symmetry? Yeah. It's symmetric over the y-axis. That means it's even. So we were told to describe it in quadrant 4. Just like part B, in quadrant 4, it is always decreasing. So in quadrant 4, we decrease.
You can make it into a little cat face, draw 2 eyes.
You could, but I don't know if I'm that cute today. Not drawing any cat faces today. But yeah, it does kind of look like whiskers. So we decrease in quadrant 4, goes through 0, 0. And you can see from the picture that it is an even symmetry. So we said I spelled symmetry wrong the first time? 1M? Tell you what, we'll put it both ways in the notes so we know at least one of them's right. Okay? Is B undefined? What do you mean? Because it doesn't have any symmetry. Because it doesn't exist in quadrant 4, or 3, excuse me, it has no symmetry. We can write no symmetry, but if I do that, now I'm only going to be right either 1/3 of the time or 2/3 of the time, and I blame you for that. I'm going to go with 2 M's. It feels more right.
M's. I searched it up.
How many M's is it?
2.
2. Okay, I was right 2/3 of the time. Woot.